Hi, I'm Norman Wildberger. In our last video, I outlined a basic framework for this new way of thinking about hyperbolic geometry. Now we have to do some legwork and set up a framework of coordinates so that we can prove these various things and a lot more. Ultimately, we're going to be working with projective coordinates, but it's better, I think, to start with a more familiar coordinate system, that of Cartesian geometry in the plane, which I hope was familiar to all of you from high school geometry and college geometry perhaps. So let's today review some basic things, make sure that we're agreed on some notation, and let's write down some fundamental theorems that we're going to be using over and over again as we proceed. So today is going to be pretty elementary. We're going to talk about the Cartesian coordinate system with x and y axes, labels as usual, so that a point, say A, is a pair of numbers, an x coordinate and a y coordinate, and let's agree that we're going to use square brackets for points. So this one here is the point 3, 1, because it's 3 over in the x direction and 1 over in the y direction. While this is 1, 0, and this is minus 1, minus 1. A line, on the other hand, will be represented by a linear equation in x and y. Something in the form ax plus by equals c. And this particular equation is x minus 2y equals 1. And I remind you that that means that all the points on the line satisfy this equation. Now, instead of writing this equation all the time, or say this one here, we're going to use a little bit of a shorthand and just record the three coefficients that are occurring. Coefficient of x, the coefficient of y, and the number which is on the right-hand side. And we'll record that triple as a proportion, because it's really only the proportion between those three numbers that matters. In other words, if we multiply all three numbers by minus 1/3 or anything else, then the equation is really the same equation in terms of the points that lie on it. So here's our convention for the equality between two proportions. You're allowed to multiply the three entries by any non-zero scalar, and you get the same proportion. So the equation x minus 2y equals 1 gets represented by the proportion 1 to minus 2 to 1. And so that's how we're going to talk about this line. We're going to say that this is the line 1 to minus 2 to 1, written in round brackets. Now I must warn you about a little bit of a difference in the convention here and in my book or in my Wild Trig series. In the book, in the Wild Trig series, I use pointed brackets for lines, not round brackets. And the only difference is that the pointed brackets is the same as this one except for a minus sign in the third part, or in the third number there. So what we're calling round brackets 1 to minus 2 to 1 would in my book be written as pointed brackets 1 to minus 2 to minus 1. You might ask, well, why am I using this new convention? The reason is because we're dealing with a new geometry here. This is going to be hyperbolic geometry, and this convention is exactly suited to hit hyperbolic geometry on the head, while this convention exactly works best for Euclidean geometry. Okay, so it's not that one of them's right or one of them's wrong. We're going to use this convention for hyperbolic geometry and the pointed brackets one for Euclidean geometry. Now, any 2 points in the Cartesian plane, if they're really 2 points, that is if they're different, determine a line. The line through 2 points theorem says that for any 2 points A1, x1, y1, and A2, x2, y2, there is a unique line L that passes through them. And here is the line L, depending on these 4 numbers. So it's the line round brackets y1 minus y2 to x2 minus x1 to x2 y1 minus x1 y2. So this is maybe a little bit of a novel idea for those of you who have done high school geometry. You will all have done exercises where you're given 2 points and asked to find the line through them. Maybe the point 1, 2 and the point 5, 7. What's the line that goes through them? So you all know how to do that. This is one step up from that. It's saying, suppose we have a general point x1, y1 and a general point x2, y2. What's the line joining them in terms of those numbers x1, y1, x2, and y2? So it's the same idea, except that instead of working with particular numbers, you're working with abstract numbers or variables. And the result is that you're getting a formula that has more meaning than it does when you work with particular values. So this is a very nice formula, because once you've seen this formula, you can hope to remember it, and then instead of having to do the computation each time, you can just sort of plug into the formula. It's going to be a major theme for us, that we want to somehow think not in terms of algorithms for doing something, but rather in terms of formulas for the outputs of those algorithms. It's ultimately the formulas that algorithms yield which are the real substance to our theory. I'm going to leave this as an exercise to you. Okay, so exercise 5.1, write down proofs of these. So write down a proof of this theorem. And this one here, the collinear points theorem, which follows from it, that if you have 3 points, A1, A2, and A3, with coordinates x1, y1, x2, y2, and x3, y3, then those 3 points are collinear precisely when this combination of 6 terms equals 0. x1, y2 minus x1, y3 plus x2, y3 minus x3, y2 plus x3, y1 minus x2, y1 equals 0. So to give you a hint as to how to do that, well, you could take this line that joins A1 and A2, and then the condition that x3 lies on the line is just the condition that x3 times this plus y3 times this equals this. If you write that out, bring everything to one side, you should get this. This little quantity here, these 6 terms with plus, minus, plus, minus, plus, minus sign, that's going to be quite an important quantity in planar geometry, but also for us. And let's make sure that we all at least know a little bit about determinants. Determinant is a very important function in mathematics. In fact, it's the most important function in mathematics. It's a function that takes a matrix and outputs a number. And here are the definitions of the 1 by 1, 2 by 2, and 3 by 3 determinants. So the determinant of the matrix, which just has a single entry A, is just A. The determinant of the matrix A, B, C, D is AD minus BC. And the determinant of the matrix A, B, C, D, E, F, G, H, I is this combination of 6 terms. AEI minus AFH plus BFG minus BDI plus CDH minus CEG. And then there's also 4 by 4 and 5 by 5 determinants, and it gets more and more complicated as you increase the size of the matrix. So there's a lot to be said about determinants, and here are a couple of videos that you can have a look at to find out a little bit more about them. The Wild Trig 70 is talking about determinants in geometry, and the Wild Lin Algebra number 4 has a lecture on area and volume in which determinants figure prominently. You should probably also know that a determinant like this can be rewritten in a number of different ways. So here's one way of rewriting it. Please check that it's actually equal. It's as A times this 2 by 2 determinant here, and then minus B times this 2 by determinant, the one obtained by eliminating the row and column through B, di minus fg, plus C times this 2 by 2 determinant, the determinant of that 2 by 2 block. Or another way of doing it, sort of expanding it along a column, is to write it as A times this 2 by 2 determinant minus D times this 2 by 2 determinant, and plus G times this 2 by 2 determinant. In fact, you can go down any column or across any row, and there's a corresponding rewriting of this fundamental combination. This is a very rich, lovely little combination of letters. And the fact that there's 6 things here and alternating plus and minus should remind you of that previous expression. And here's a little exercise. Show that the determinant of this particular 3 by 3 matrix, 1x1y1, 1x2y2, 1x3y3, is exactly that little combination that appeared in the collinear points theorem on the previous page. So we're going to learn a little bit more about determinants as we go along, but please become familiar with some basic things about determinants, if they're new to you. A natural question that many of you might be asking is, what number system are we working with here? Many of my examples only involved integers, like natural numbers 1, 2, 3, or their negatives, or 0. But in fact, we generally want to work with rational numbers. So the rational number system, a rational number is a fraction like a over b, where a and b are integers. And b, the denominator, is not allowed to be 0. And there's an important notion of equality between two such rational numbers, that a over b equals c over d, precisely when AD equals BC, or in other words, when AD minus BC equals 0. So for example, 1 over 3 is the same as 2 over 6. So to start with, let's think in terms about rational numbers. We can do hyperbolic geometry, it turns out, over any field, not of characteristic 2, whatever that means. But it's better to start thinking about it in terms of rational numbers, and that's how we're going to start. Later on, we're going to see that the theory is completely general and it works for finite fields, works for complex numbers, works for a whole variety of interesting things. But to start off, we're really only using rational numbers and the 4 basic operations of addition, multiplication, subtraction, and division. Alright, now I'm obliged to say here rather quickly that the usual attitude to real numbers in modern mathematics is a distortion, and it's cheating in actually a major way. Real numbers, the way they're currently set up, don't really work logically. And this is a source of inaccuracy and confusion that infiltrates many, many different branches of mathematics, unfortunately. Now, I'm going to deal with all of that in my Math Foundation series. So eventually in that series I'm going to explain all about real numbers and the problems that currently exist with them. But let's just say now, as a general orientation, that working with rational numbers is at least 1,000,000 times simpler than working with real numbers. Or real numbers are at least 1,000,000 times more complicated than working with rational numbers. I'm not exaggerating here at all. Okay? The difference between these levels is incredibly big. Okay? To do real numbers properly, well, it's just such a huge, huge amount of work, which is almost never done properly anywhere. That's why all those textbooks, whenever they get to real numbers, they sort of mumble under their breaths and talk a little bit about axioms here and wishful thinking there, and nobody actually ever writes down exactly what real numbers are and exactly what the operations are and exactly what the proofs of the various laws are that supposedly exist for them. So this is one of the big advantages in our approach to hyperbolic geometry, in fact, in our approach to geometry generally. We're concentrating on the rational numbers. And remarkably, the theory works beautifully just with the rational numbers, as you'll see. Just as we had a condition for 3 points to be collinear or on a line, So we are looking for a condition for three lines to be concurrent. That means we have one line like this, another line like this, another line like this. They're all passing through a single point. And here's the condition in terms of our three lines. So expressed now in terms of our proportional representation. Remember, these are the coefficients. This is a1x plus b1y equals c1. And similarly for L2 and L3. The theorem is that if these things are concurrent, then this particular determinant, the determinant that you just get by writing down the three proportions along the rows, and there's that determinant, that it should be equal to 0. And the proof is essentially just a little bit of linear algebra. If you have a point xy which lies on all three lines, then it means that this system of equations has a non-zero solution. Namely, the solution xy, which is the point we're talking about, followed by -1. That -1 there makes sure that the c1 ends up on the other side. So if xy lies on all three lines, then this system has a non-zero solution. And by elementary linear algebra, that means that the determinant of coefficients here, which is this thing here up here, has to be 0. And just as two points determine a unique line, so two lines generally determine a unique point, the meet of the two lines. However, there's a bit of an exception there. The two lines could be parallel. If they're parallel, then they actually don't meet. So we need this idea of parallel to talk about the exception to when two lines don't determine a point. Here's the definition. The lines L1 equals A1, B1, C1, and L2 equals A2, B2, C2 are affinely parallel precisely when A1, B2 minus A2, B1 equals 0. So it's really only the coefficients of x and y that matter in the equations for both lines. And what we're really saying is that these two coefficients are proportional to these two coefficients, then the lines are parallel. And I'm introducing this affinely parallel terminology here because later on in hyperbolic geometry there's also a notion of parallel, which is different from this one. So we're only adopting this terminology temporarily, so to speak. Later on in hyperbolic geometry there will be a different notion of parallel. Here is the point on two lines theorem, which says that if the lines L1 and L2 are not parallel, then there's a unique point A which lies on them both. And in terms of these coordinates for the lines, here is the point, which we'll write as L1, L2, which lies on both lines. So it's a kind of a ratio of determinants there for both coordinates. This is B2C1 minus B1C2 divided by A1B2 minus A2B1. And this one is A1C2 minus A2C1 divided by A1B2 minus A2B1. And this denominator here, well, that's exactly the condition that we were trying to avoid. If the two lines are parallel, then this would be 0. And if they're not parallel, well, then that's not 0, and it actually makes sense. And I'll leave it to you as an exercise to prove this by solving for the two lines. There are the lines L1 and L2, and what we're looking for is when there's a unique point on them. If they're not parallel, that means that this equation and this equation, they're not really multiples of each other, and then we can solve, and this is the point of intersection. We call it the meet of the two lines. So if those theorems weren't reasonably familiar to you, then you probably have some catching up to do. I suggest that you work through some examples. Always a good way to start. Just draw a picture of the plane, draw some points, compute some lines, compute some intersections of lines, verify the various theorems in particular cases. That's a good way of familiarizing yourself with formulas. Okay, now let's move to the main object of interest, which is the unit circle. Remember, hyperbolic geometry is really the study of one particular circle. And now that we have coordinates, we might as well choose a very natural and sort of familiar circle. We're going to choose this circle here, x squared plus y squared equals 1. That's going to be our basic circle that we're calling C, or that sometimes we're calling the null circle. And now we're going to look at this important theorem that we can parameterize points on this circle. It's called the parameterization of the unit circle theorem, and it says that every point on the unit circle is either minus 1, 0, which is this point right over there, or it's in this form. It's 1 minus t squared over 1 plus t squared, 2t over 1 plus t squared, for some parameter t, for some number t. And this picture here is explaining where this thing comes from. Okay. The significance of t is that it's the coordinate on the y-axis such that the line through minus 1, 0 and this point 0t meets the circle in the second point, that one there. So it's a computation that if you compute the equation of the line going through this point and this point, compute the equation of that line, and then solve for where it meets the circle in the second point, then you will get this point. Okay, it's a very important computation, and so I'm going to refer you again to Wildberger 14, Rational Parameters for Circles, where you can see that I will slowly, carefully go through this argument. There's no need for me to repeat the argument here. Okay, so have a look at Wildberger 14, Rational Parameters for Circles. And I'm going to introduce a little bit of terminology here. Let's call this point E of t. So for t varying, E of t varies on the circle. And I'll make a little bit of an ambiguous comment here, or note, that the point minus 1, 0 can also in some sense be viewed as an E of something, namely E of infinity. Okay, if t is a very, very big number, like a million or something, then this is almost minus 1 and this is almost 0. So as t varies, or t approaches infinity, either from the positive or the negative direction, either way this pair approaches minus 1, 0, and so in some sense this is also included in this framework, but with an infinite value for t. Okay, it's more familiar these days to think of the unit circle as being parameterized by cosine theta and sine theta. That's almost invariably a mistake. It's almost invariably better to think of this parameterization, which is much earlier, much more fundamental, much more natural parameterization of the circle. And more accurate too, because you're actually getting points that actually truly do lie on the circle and not just near the circle. Cosine theta, sine theta will not get you points on the circle, only get you points near the circle when it actually comes down to any explicit calculation. A big difference. Okay, so this should be a major result that all high school students learn, in my view. Okay, it's one of the really fundamental things that people should know. We're going to use it a lot because we're interested in this unit circle. We're very interested in it. So let's get a little bit of experience with this parameterization of the circle. There it is there, E of t, 1 minus t squared over 1 plus t squared, 2t over 1 plus t squared. If t equals 0, then you're getting the point 1, 0. That's right there. That's E of 0. E of 1 is just that point. E of minus 1 is that point. E of a half would be around there. That's exactly what you get when this coordinate is a half. And it turns out to be 3/5, 4/5. E minus a half down here. E of 2 would be here. E of minus 2 here. So between 0 and 1, we're traversing this quarter of the circle. and then 1, 2, 3, 4, 5, 6, 7, 8, 9, a million, and so on in that direction. And here are all the negative numbers. A little exercise for you. Show that if you know where e of t is, so e of t is somewhere, then e of minus t is reflection in the x-axis. That e of 1 over t is reflection in the y-axis. And that e of 1 plus t over 1 minus t is rotation by a quarter turn, otherwise known as 90 degrees. That's a nice exercise. And our last theorem for the day talks about the intersection between our unit circle and a general line. And it's the meets of line and circle theorem, stating that a line L meets the unit circle C in either 1, 2, or 0 points. A line does not meet a circle in 3 or 5 or 7 points, either in 1, 2, or 0 points. It's obvious geometrically, but it's nice to have some kind of algebraic manifestation of our geometrical intuition. So how do we do that algebraically? Well, we write down the equation of our line. Let's say it's ax plus by equals c. And the equation of our circle, x squared plus y squared equals 1. And we want to find solutions to both of these equations at the same time. So a place where the circle meets the line is a point that satisfies both equations. So we're looking to see how many solutions x, y are there to both equations. Now this first thing here is a line, and maybe I didn't say it explicitly, but when you have an equation ax plus by equals c representing a line, you must have at least one of a, b being non-zero. One of them can be 0, but both of them cannot be 0. Because then you just have an equation 0 equals something. That's not an equation of a line. So let's suppose that a does not equal 0. So if a does not equal 0 means we can divide by a, and from the first equation we get that x equals c over a minus b over a times y. And then we can plug that into equation 2. So there's x squared plus y squared equals 1. That's now an equation only involving y. It's a quadratic equation. So it's y squared times 1 plus b squared over a squared. Coefficient of y will be minus 2 times this. So minus 2bc over a squared times y. And then the things not involving y, well, there's a c squared over a squared coming from this, and a minus 1 if we bring everything to the left-hand side. Let's multiply by a squared, since a squared is not 0, and then it becomes somewhat simpler, just y squared times a squared plus b squared minus 2bcy plus c squared minus a squared equals 0. And that's a quadratic equation in y. And quadratic equations always either have 1, 2, or 0 solutions. And once you know what y is, well, then x is forced, because plug back into here, then x is determined. So it means that there can only be 1, 2, or 0 points that satisfy both equations. And how do you tell whether it's 1, 2, or 0? Well, that depends on the discriminant of this quadratic equation. Sort of the b squared minus 4ac term. In other words, if you take this coefficient of y and square it, and then subtract 4 times the coefficient of y squared times the constant term, that's the discriminant. And now please check that, pleasantly, this thing factors. It can be rewritten as 4a squared times a squared plus b squared minus c squared. It's one of these pleasant things that happens a lot in this subject. This is actually elementary but important example of a very pleasant factorization. This discriminant factorizing like this. Now 4 and a squared, they're squares. So I remind you that in the quadratic formula you have to take the square root of this. And there will be 0 solutions when this is 0. Well, we're assuming a is not 0, so that's only when a squared plus b squared equals c squared. And there's going to be 2 solutions when this is a non-zero square. In other words, when a squared plus b squared minus c squared is a square. And there's going to be 0 solutions when this thing is a negative number or a non-square. So altogether 1, 2, or 0 solutions depending on whether this discriminant is a 0, a square, or a non-square respectively. And the argument for b not equal to 0 is exactly the same, but just with a and b's reversed. Please make sure that you've gone through that argument, that you convince yourself that that works. And especially make sure you checked my arithmetic there. Alright, so an exercise, just make sure that you check that the same conclusion holds in the case when b is not equal to 0. So that the situation really is symmetrical between a and b. And here I'm just stating a corollary, a consequence of the proof of that last theorem. The different cases that result. So the line ax plus by equals c is tangent, first of all, to c. In other words, meets it at exactly 1 point, precisely when a squared plus b squared equals c squared. That's the case when the discriminant was 0. In a sense, what you really have there is 2 equal points, but they really coalesce to just give 1 point. Secondly, it meets c at 2 points, precisely when a squared plus b squared minus c squared is a square. Well, actually a non-zero square to separate it from this case here. So that's the case when you can take the square root of this thing. Right? If you can take a square root, then the quadratic formula will give you a rational number. A squared plus b squared minus c squared is a square. And the third case, that it meets c at no points, precisely when a squared plus b squared minus c squared is a non-square. So that might be, for example, when it's a negative number, but it might also be when it's a positive number, but just not a square. Remember, we're only working over the rational numbers. And it's possible for a line, say over here, it's possible for a line to look like it meets the circle, but in fact it doesn't over the rational numbers. Okay, that's a possibility that you have to keep in mind here. It's possible for this to be positive, but a non-square, in which case there will be 0 solutions, even though it may look like it's intersecting the circle. The algebra tells us whether there is a true meet or not. Now this first case, a squared plus b squared equals c squared, is particularly pleasant. That's the case when we have a tangent to the circle, or what we're calling a null line. So for example, here's a point on the circle, 4/5, 3/5, and the associated tangent to it is the line 4 over 5 times x plus 3 over 5 times y equals 1. Or if we clear denominators, 4x plus 3y equals 5. That does meet this Pythagorean triple condition, because 4 squared plus 3 squared is indeed 5 squared. That line is exactly tangent to the circle, and well, if you plug this number in here, then you will see that is actually satisfied. So this is actually the tangent to the circle at this point here. Alright, so we've reviewed and maybe extended your understanding a little bit of the Cartesian geometry associated and relevant to a study of the circle. So with this under our belts, we're now ready to go back to the formulas of universal hyperbolic geometry I told you last time, and see if we can get expressions for duality, quadrants, and spread in terms of coordinates. So that we don't have to actually work out cross ratios, we can just plug into nice formulas and evaluate quadrants, evaluate spreads, figure out duality very simply. That's what we'll do next time. I hope you'll join me for that. I'm Norman Wildberger, and thanks for listening.